So as we've seen before, an alternative to fitting models by by minimizing the residual sum squared errors is to define the log likelihood, as we saw before, and then as an alternative to a least squares fit, find parameters that maximize this likelihood value. And so we're now going to switch to talking about more complex linear models, which are going to be mixed linear models and generalized linear models. And we'll be following these two books, both of which you can download for free if you're on the campus. It's funny to say you have to be on campus because, of course, none of us are on campus right now. But if you're on the campus VPN and you go to springer.com, you should be able to get both of these books for free. This book, this linear mixed effects model using R, has lots and lots of R code to follow. It's very, very technical. It reminds me a little bit of the Nieder book. It's a very good reference. It's very thorough in its documentation, and it's a little bit dry. This book, mixed, the Zur book, which I will sometimes refer to as the penguins jumping off a cliff book, the mixed effects models and extensions in ecology with R, is a little bit less mathematical in its treatment. It's a little bit more accessible and more readable. So by going back and forth between these two books, you can get a pretty good sense of how to use these more complex models, which, as we'll see, can be important for real biological situations. So to start with the Glagge book, we can summarize our linear regression. So this is a slide that we've seen essentially over and over again, that we have our multivariate linear model. We know that the residuals are normally distributed with a mean of 0 and a variance of sigma squared, whatever the residuals are. We know that every data point is equal to the model, right? So that's y hat plus the error. The expected value is the regression line, so that's the model. And the variance, of course, is just the variance, which is sigma squared. So we have talked about how you can define maximum likelihood as an alternative to least squares for finding parameters. We're just going to state this without proof. It's going to turn out that if you're a smart person, so we'll take it that smart people tell us, that you can write down this log likelihood function. So this is the definition of the log likelihood function, which you can see is, of course, very closely related to just the normal distribution itself. And of course, if you maximize that, you can get a fit that for a simple linear model is equivalent to a residual sum square fit. And so this textbook goes through and derives this maximization of this maximum likelihood estimator. And of course, for the simple linear squared residual, it turns out to be the same form as the residual least squares fit. Now, again, it's not going to be true for the more complicated models that the residual sum square fit is going to be the same as the maximum likelihood fit. But both of these textbooks tend to emphasize the maximum likelihood fit more than the residual sum square fit, and they use this formalism to describe the way that the models work. Let's think about a little bit more about the assumption of equal variance, the assumption of independence of all the data points, and look at ways that we can relax this assumption to try and deal with real biological situations where we know the biology of the situation is going to require us to deal with samples where the assumption of independence is not appropriate. So let's think about sort of formally expressing this assumption of equal variance in terms of covariance matrix. So as we saw before when we were talking about PCA, right, we define the covariance matrix, right, as a matrix in which the diagonals are the variance and the off diagonals are the covariance. Right? And in particular, the covariance matrix, so here's again our definition for covariance of xi minus x average, yi minus y average. One fact that's true about covariance is that if you have two variables that are independent, the covariance approach is within numerical round off of 0. Okay, so this is going to be a useful fact about covariance. It's going to allow us to express mathematically this one way in which samples can be independent, right? So if I have one vector here and another vector here, and there's no relationship between them, right? On average, this is going to come out to 0. And when I take the covariance of A and B, that's going to approach 0. And so we think of this is an expression of the assumption of the way the errors are distributed for our standard linear model, and we can think of this as being a covariance matrix, right? So if I have n samples, I have n samples here and n samples here, and I'm going to use this covariance matrix to express my beliefs about the assumptions of independence or the appropriateness of assumptions of independence of this covariance matrix, right? So if I sample any one sample, if I have any one of my samples, right, and I were to sample it over and over again, right? So consider a regression line, right? And so we have our regression line, right? And if my drawing is working a little bit better here, we have a regression line, right? So we have some regression line that looks like this, right? So if I have this one data point on my regression line, if I sample that over and over and over again, what that tells me is that what I know from the assumptions of the linear regression is that the sampling this over and over again, I'm going to expect some kind of normal distribution centered on the regression point, right? And the variance of this normal regression, the variance of sampling this over and over again is just going to be the variance of my regression. It's going to be my sigma squared, right? But now consider 2 points, right? A point up here and a point over here. The assumption of independence says that if I sample this one over and over again and this one over and over again, because these are independent of each other, right? They're two different samples. I'm not sampling the same one over and over again. I'm sampling these same two. So if I sample this one an infinite number of times and this one an infinite number of times, the assumption of independence here is that the covariance is going to be 0, right? Independence means that this one and this one, they don't know about each other. So when I sample them over and over again, the variance is not going to be sigma squared, it's going to be 0. Right? And so we can think about expressing the way for every linear regression that we've seen so far, we have an assumption of equal variance, and we're going to express this now for 2 different kinds of samples. If you sample the same sample over and over again, right, then that's like the diagonal here, right? So this is sample 1 and this is sample 1. So if I sample, if instead of just having one sample, if my first sample in the data set, if instead of just sampling it once, I could somehow sample it an infinite number of times, the distribution of sampling that an infinite number of times would be sigma squared. But if I have 2 different samples, if I could somehow sample them an infinite number of times and measure the covariance, that covariance would be 0 because there's an assumption of independence. Right? That assumption of independence is that this data point doesn't know anything about that data point. And so a mathematical way to express that is that the covariance of sampling these two is equal to 0. Now, this is like a lot of frequentist statistics. This is sort of involved. There's a kind of fantasy element to this, right? So we're sort of imagining that even though, right? So in a normal linear regression, I just have a bunch of data points, right? I don't sample any of them an infinite number of times. I sample each one of them once, right? But frequentist statistics always has this sort of element of some fantasy to it, which says, well, the assumptions of the frequentist model are that if I somehow could sample these an infinite amount of times, then anytime I sample the same one an infinite amount of times, I'd be on the diagonal here, the variance is going to be sigma squared, and anytime I sample 2 different ones an infinite number of times, I'm off the diagonal, and the variance is going to be 0. Okay, so we're doing a lot of work here to try and capture mathematically in this covariance matrix what we mean by independence, and of course that's going to allow us to relax this assumption of independence when we get to mixed linear models. Okay, so let's demonstrate why we need mixed linear models, why we need to think about this assumption of independence by making a data set in which the assumption is violated and showing that our inference is sort of hopeless in the situation using a standard linear model. So this is our code that's here. You can download it and examine it if you care to. It's going to produce data that looks like this, where you have 6 hospitals. And every odd hospital is assigned to drug 1, and every even hospital is assigned drug 2. And then you measure something about the patients in those hospitals here on the y-axis. So maybe it's their weight or age, or their change in weight or age, or whatever, right? So you have something that you're measuring in the hospitals. You have 6 hospitals. Each hospital, like 3 of the hospitals are assigned drug 1, and 3 of the hospitals are assigned drug 2. And importantly, in the way we've simulated this data, there's a hospital effect, right? So each hospital has its own effect. So the hospitals are different, but the drugs are not different, right? The drugs are just sampled from the hospital. The actual data is just sampled from the hospital, right? So when we actually generate the data, the drug is not used in any way to generate the data. So the null hypothesis for the drug is always true, right? But if you were to model this, so our assumption of independence is not correct here, because drugs and hospitals are confounded with each other. Right? But if you were just to plot this out and look at it, right? So ignoring right, the assumption that the null hypothesis with drugs is always true. Right? But if we were just to plot out drug 1 by drug 2, ignoring the hospital effect, it would look like there's something that's different here. And moreover, if we build a standard linear model, now this is a disastrous linear model, right? This is hospital is nested, or drug is nested within hospital, right? So these are not linearly independent columns. These are confounded columns because drug is nested within hospital, which means that this is a numerically unstable model. And as we'll see for this numerical and unstable model, it produces disastrous inference, right? So here. I use just an ANOVA test to say, is there a drug effect? And the model says there's an enormous drug effect, right? But the model is just incorrect. This is just incorrect inference. The model is saying that there's a drug effect, but it's confusing the drug effect for the hospital effect, right? And so this is an example where we are in violation of our assumption of independence, and we have a complete disaster, right? We're reporting significant results for one thing, but in fact they're being caused by a confounding variable, and our statistical models are just not appropriate for the data that we have. Right? So we want to try and use mixed linear models as a way to relax this assumption of independence, and allow our model to know that that patients are nested within hospitals, and that there are hospital effects that the model should be looking at, and not confuse those hospital effects with drug effects. And so we're going to add to our variance covariance matrix. So instead of having zeros on the diagonal, which says that these are independent, we're going to have a situation where we have another parameter, which is I think that's phi or phi. I don't know. Those of you who have fraternities could look up what that is. But we have this other parameter, which is this parameter here, right? That's going to be our variance covariance matrix is going to be whatever this parameter is if the patients are in the same hospital, and otherwise it's going to be 0. Okay. So if patients are in different hospitals, then we don't expect there to be any relationship between the covariance of those patients. But if they're in the same hospital, instead of having the value on this variance covariance diagonal be 0, it's going to be this parameter that's here. Okay, so when we go from a mixed linear model, we're going from a variance covariance matrix that looks like this to one that looks like this, where off the diagonal on the variance covariance matrix, if the patients are in the same hospital, you have this parameter which is non-zero, but if they're in different hospitals, then it equals 0. We'll state without proof, again, coming now from this textbook. This is from the Gillespie textbook, which also states this without proof. So I've never been with this proof. So this really is, I've never been through these proofs. So this really is the smart people tell us. We will have to take on faith that this derivation is correct. But when you switch to this new variance covariance matrix, the likelihood function goes from this to that. And so it goes to something that's much more complex. And then what the mixed linear models are going to do is they're going to fit this likelihood function by maximizing the likelihood of this likelihood function that's here. And again, I think it would probably take a fair amount of time to for me to dig up these proofs and for us to go through them in detail. So we're just going to assume that the people who built these models know what they're doing, and that this is in fact the likelihood function, and that when you maximize this likelihood function, you're able to fit the model with this new additional parameter, which is off the variance covariance matrix, which again is this additional parameter is the off diagonal parameter that tells you how correlated two samples are if they're in the same hospital, and is this parameter here, and is 0 if you are off the if you're for two samples or for two patients that are not in the same hospital. So this is going to allow us to nest the individual patients within hospitals and allow the model to know that there's this correlation that it should expect to see within hospitals, but that the assumption of independence won't be true for subjects within the same hospital, but will still be true for subjects across hospitals. And so R has a really nice syntax to allow us to capture this idea, right? And so here's our standard linear model where we say that drug and hospitals are canonical variables within our linear models. But R instead says, well, you instead want to say, right, what you're interested in for inference is there an effect between data and drug, but we want hospital to be a random variable, right? So a random variable is this term in mixed linear models that says, well, we actually want in our data set we want there to be one degree of freedom that describes hospitals. So even though we have 6 hospitals in this, right? So in our standard model, there's 6 hospitals in this data set. So in our standard model here, we lose 6 degrees of freedom for hospitals because there's a dummy variable, right? And this model is basically assigning one dummy variable for each hospital, which we know is the column vectors of zeros or ones if you're that hospital, if you're not that hospital, right? But this in the mixed linear model, hospital is instead it's a different kind of variable. It's called a random effect. Is the terminology, and it says it says instead of using 6 parameters to describe the effect of a hospital, even though there's 6 hospitals, have this one parameter. So we're going to assume that the correlation between all the patients in each hospital is the same, right? So if you have hospital 1, hospital 2, hospital 3, hospital 4, hospital 5, and hospital 6, within each hospital, the correlation coefficient that describes how well how well data from each hospital how tightly data from each hospital is correlated within the hospital, that's going to be this one variable here, right? And so there's this one variable that describes these 6 hospitals. You only lose this 1 degree of freedom, and this one variable, instead of being a canonical ANOVA variable where the coefficient, where there's a dummy variable multiplied by each coefficient, this one variable describes, basically for any 2 samples, are the samples in the same hospital, in which case the correlation coefficient is between the hospitals is this variable here, or are they in different hospitals, in which case the assumption of independence still holds. And so this is how we tell R that this is this special kind of variable that we don't want modeled as a canonical variable in a linear model. We want it modeled with this special correlation coefficient that is expressed as a lack of independence for some but not all of our samples. That's expressed as the off diagonal and the variance covariance matrix that describes the residuals. So we put this into R. But then we can, this model, once it's here, we can still use an ANOVA to get a p-value here. And when we do that, things get a little bit better, right? So this is actually not working perfectly yet. So we go from having horrifically bad inference to maybe just sort of marginally bad inference, right? So the mixed linear model here didn't do a great job of perfectly controlling for the hospital effect, but it did a better job than just ignoring the problem at all, right? So this assumes independence of the variables of drug and hospital. That led to calamitous inference. When we relaxed that assumption of independence for some of the hospitals, the model wasn't really able to capture what was happening in our data very much, but the inference is certainly better than just ignoring the problem. So it turns out there's another way to think about this is a mathematically equivalent way to formulate what's going to be called our nested experimental designs. This is the first time we've really heard about this phrase nested, right? But the idea here is that our data are nested within hospitals, right? So we have this fixed effect, which is whatever the drug is doing, and then there's a nested design because there's groups of subjects within hospitals, and it's a nested design. Because some of the hospitals have drugs and some have drug 1 and some don't have drug 2, right? So kind of you have one set of nests here, which is drug 1, and another set of nests, which is drug 2. And so this particular design can be analyzed really nicely with these series of linear models, which are called the mixed linear models. Right? And so a mathematically equivalent way to describe the models, these mixed linear models, is we say the variance within each groups are equal, right? But that's again, you can think of this as saying, right, this is the variance covariance matrix that describes all of the residuals, right? All of the errors in our model, right? And so to say that within each group the variance is equal is to say that there's this one parameter within each group that describes the residuals when they're in the same hospital, as opposed to when they're in different hospitals where there's an assumption of independence, and so the covariance of any 2 samples within the same hospital is going to be 0, right? So the covariance of any subjects within the same hospital the covariance of any two subjects within the same hospital is this variable here, and the covariance of any two subjects within different hospitals is 0, right? Which is to say that there's one parameter with equal variance across all the different groups. So no matter how many different hospitals you have, you can describe the variance within each hospital by one parameter, right? And moreover, the effect of each hospital is normally distributed with a mean of 0. So you can think of each hospital, right, as adding to the effect of the drug, right? So some hospitals make the Y value for the drug go up. Some hospitals make the Y value for the drug go down. So it will turn out, and this again will state without proof, so this is going to be smart people tell us, but that the mathematical description that we've been describing is equivalent to saying that those hospital effects, which you add to the drug, are normally distributed with a mean of 0. So this fixed effect is just like a standard linear model, right? There's a B0 here. We're going to get a B0 that's going to, in our maximum likelihood fit, make the error as small as possible. That is to say, make the model as probable as possible. But this hospital effect, this random effect, is a new kind of variable, which is described as a parameter in the variance covariance matrix, as opposed to the parameter that's described in our standard linear model. So we can express this second way of thinking about the data. It's again mathematically equivalent. So really, it to first approximation, it doesn't matter which of these libraries you use. Although you'll see that we actually get very different p-values from the two formulations that are in R, and we'll explore in a slide or two why that happens, right? So here. I just changed to a different library. So these are two different libraries that have the same mixed linear models in them. You can see that the way that I'm invoking these libraries is almost the same, except that here I just say the random variable equals that. I say that the data are nested within hospitals, and I express that for the LME package here, as opposed to using the syntax here. But otherwise, it's much the same idea. But even though this is much the same idea, we'll see that the p-values come out really different. Okay, so actually this is a little bit confusing, right? So here are the AIC, BIC, and log likelihoods of the models under the two different libraries, and you see those are identical, right? So you'll remember AIC, BIC, and log likelihood from our previous lecture. So those are all identical. We can see that the values of the parameters themselves are identical, right? And we can see that the p-values here using the t-distribution are identical, right? So when I get the p-values from the t-distribution here of the parameters of the null hypothesis that these parameters are equal to 0, those are identical. Okay, but what's really surprising is that when I use the ANOVA formulation to get the p-values here, I actually when I use that ANOVA formulation to get the p-values, I actually get really different answers, right? So the ANOVA formulation based on this formulation, based on the second formulation, I get what looks like a much more reasonable answer than when I use the ANOVA on this formulation. And you might say, well, how can this be, right? So both models say this isn't significant if you use the summary view, right? And you get actually not identical, but very similar p-values using the summary view. But it seems like I get really inappropriate p-values here when I use the ANOVA formulation. But on what is essentially an identical model, I get what looks like a much more appropriate set of p-values using the second formulation. And you might say, well, how can this be? But the answer turns out to be that the models consider the degrees of freedom differently, right? And so you might think, well, isn't the degrees of freedom just the number of samples? But when you drop the assumption of independence, the estimating the degrees of freedom is a little bit tricky, right? So consider you have two hospitals here, right, with super tight correlation. Are there 10 independent data points, or are there 2? Right, and you could probably argue that really there's closer to two degrees of freedom, because if you know there's perfect clustering within each hospital, right? If I tell you this one data point here, you already know the other 4, and if I tell you this one here, you know the other 4, right? And so the way these models estimate the degrees of freedom is different, and that causes the ANOVA model to give different values when you use the ANOVA for the p-values. So a useful metric is what the Zur book, remember the Zur book is the penguins jumping off the cliff book, calls the interclass correlation coefficient. And this is the value. So we have this value psi in our covariance matrix, which measures the degree. Again, it measures the degree of correlation within each group, right? So how tightly correlated are all the patients within the same hospital? And so this value rho that you get in summary here is defined as that value divided by that value plus the variance. And so you can sort of think of this as what is the ratio of how tightly the subjects within each hospital are correlated with each other, divided by some estimate of the total variance associated with the model. And so the Zurbuch makes some arguments about how this what the effective sample size is depending on these variables, right? So as this value goes up, you have more tight correlation within each group, and the effective degrees of freedom goes down. But as this goes to 0, then the degrees of freedom just approaches the number of samples, right? And clearly for the ANOVA formulation of the effects of the drug, the degrees of freedom is important because the differences in the degrees of freedom between these models impact the way that the F statistic is interpreted in the ANOVA and lead to very different results in our modeling. So generally, if you're not sure which one to use, this formulation, what we're calling the m.mix model here, the LME formulation, seems to be more robust and gives you more conservative results from the ANOVA. So this is probably the one to prefer if you're using if you're going to use these mixed linear models. So in order to demonstrate this, let's consider a hospital effect where we make the hospital effect much bigger than the drug effect. So the hospital effect is really big here, or not the drug effect. That the error of sampling is small relative to the hospital effect, right? So here there's a hospital effect, and we sample that with a small standard deviation, but the hospital effect is itself really big, right? So we make the hospital effect very, very big relative to the variance of each data point, right? So we're making this value really big relative to the ratio. So this ratio is going to be close to 1, right? So when we do this and we ask for the rho, we get a number that's close to 1, right? Because the hospital effect completely dominates the sampling effect. When we instead make the hospital effect very small compared to the sampling effect, so here basically the variance of sampling is extremely small relative to the hospital effect. So our data looks like this. There's essentially is no hospital effect. And when we ask R for the rho here, it's going to be much closer to 0. So in this case where the hospital effect is really, really strong, right? So here we have the hospital effect being super strong. Rho is close to 1. Our standard linear inference breaks completely. The ANOVA from the GLS model still breaks a little bit, or maybe not a little bit. It breaks a considerable amount, but it's still better than the standard model. And again, our mixed linear model formulation, right, coming from the LME library. The mixed linear model coming from this LME library that's here seems to do much better on this data set, right? Gets us closer to a uniform distribution. Although interestingly, it's still not perfectly uniform, right? So none of these models are really able to deal with the data that we have. If we make the hospital effect small compared to the drug effect, rho tends towards 0. And here actually, interestingly, our mixed model now, like our standard linear model does fine, right? Because making the rho 0 means that they're actually, the assumption of independence is appropriate, right? So our standard linear model assumes that rho equals 0. We have a data set here where rho basically is 0 because there's no hospital effect. So as the assumption of independence becomes more and more appropriate, our standard linear model starts to do fine, right? Because there's the assumption of independence is appropriate for these data. Interestingly, this formulation of the mixed linear model still breaks. So really, there's just no reason to use the ANOVA on this first formulation of the linear models. But this last formulation of the linear models actually now becomes somewhat conservative, right? So you can see that none of these models are perfect under all conditions, right? You can find conditions in which all of these models break, either becoming too conservative or not conservative enough. So our conclusion is that mixed linear models are really useful, but they're a bit fragile, and we should always approach the interpretation of their p-values with some caution.